I would like to welcome you to the next session. And we decided that the first session was going to be in Danish, and then we decided the next session is going to be in English today. So, and I have to translate senior scientist Ib Lundgaard Rasmussen's title of this talk. It must be something like "Does Life Origins from Comets?" And if he assumed that he would have a more appropriate title, he can give it. We would like to thank you for coming, Ib, and we'll wait till this work. Okay, welcome.
Okay, I've been asked to do the entertainment part before we get the presentation to work. My name is Rosetta Suensson, not Rosetta. I know people mix me up, but I'm actually Rosetta Suensson, and I work as a communication officer at the European Space Agency in Netherlands. And one of my responsibilities is to take care of the Nordic countries. So together with the member states, Finland, Sweden, Norway, and Denmark, I decided to have a truck, which you can see outside, to travel around and talk about a mission to a comet. And this is what we are here for today. It's to talk about this mission with two people from Denmark who are responsible and engaged in this mission. And Ib is one of them, and I know that he's working on his presentation to get it up running. We have already traveled about 3,000 kilometers with this truck. And if you come inside and visit us, you will see a comet landscape. You will see some presentations from ESA and from Denmark. And you will also be able to see a model of the satellite. There is a small model on the table here, but you will see a bigger model. The satellite itself has a solar panel set on each side, and they are about as long as the truck you see outside. So please come out and have a look. And the satellite itself is quite large, so you will get a better dimension of what we are talking about. We will continue our journey, so if you have friends or Twitter or do anything, please let them know, because we will continue to Linköping, and then further from Linköping to Södertälje, and then back to Finland again. In total, we have counted that we will do a travel of about 4,500 kilometers just to talk about Rosetta and the mission to the comet. And with that, I will stop, because it looks like we are getting ready to have a presentation from Ib. Thank you very much.
My name is Ib Rasmussen. I'm going to talk about the question whether life originated in the comets, which is one of the questions we hope to find an answer to when Rosetta rendezvous with Churyumov-Gerasimenko, which will take place in the fall. this picture is a little disproportionate because the comet is 5 kilometers, whereas the satellite is only 3 meters. So anyway, it's the first time we plan to put a soft lander on the surface of a comet. And one of the things we could learn about is, did life originate with help from the comets, on the comets, or whatever? So where did life actually begin? Was it a local process? Did it originate on Earth? Totally unaided? There are several possibilities that have been discussed. Black smokers on the ocean bottom, a couple of kilometers below the surface, or a tidal pool where water evaporates and the impurities concentrate and a soup is formed where life slowly emerges. So that's one way of looking at it. The other is to say, did it come from the outside? Are we not alone? Are we part of a greater system? And if life did come from the outside, how did it arrive? Was it some kind of panspermia? An idea already originated with Anaxagoras in Greece, also proposed by Arrhenius in the beginning of the 19th century and by Fred Hoyle in the last part of the 19th century. How did it arrive? Well, in science fiction, of course, a spaceship will arrive and put life on Earth, a big zoo. But advanced organisms is not what it looks like in the historical record. We start with primitive life on Earth, and it develops to more and more complicated. So let's cross out the advanced organism. What about bacteria? They can travel in space. They can survive for years in space. And the idea got a boost when we discovered this Martian meteorite in Antarctica, which among many things it contains also has some interesting structures that could look like it was fossil remnants of bacteria or something like that. This has been debated for a long time, and the consensus is now that it probably is not traces, fossil traces of life, because we can see similar structures being generated in volcanic materials, and volcanoes is perhaps not the best place to start life. So I think by now it's only the group that discovered this meteorite that still maintains that it's a sign of life. So where did it begin? Now we will do it once more. Then we run through it again. There's a third possibility. Life originates on Earth, but with help from outside. With organic molecules that arrive somehow, and we know they do arrive. We know they are generated in space. We have seen sugars and alcohols in molecular clouds, and if we look at carbonaceous chondrite, a meteorite, one of the oldest, this is Allende. There are some other samples, Murchison from Australia, Tagish Lake from Canada, and Maribo from you know where. It contains a lot of carbon molecules, chondrules, calcium, aluminum enclosures, and it also contains amino acids. Amino acids, we use 20 amino acids to generate all the proteins, to generate everything that involves life. And amino acids has one special feature. They come in two shapes, just like gloves or shoes, right and left. And the important part of it is that any amino acid that goes into organic systems is of the left turning type. When you shine light through a solution of amino acids, you will see the polarization turns counterclockwise. And that happens with all the amino acids that enters into the to the buildup of organic molecules. How do the amino acids look in Allende? In Allende, there are both right and left molecules, but there is a predominance of the left-turning molecules, which points to the possibility that the idea of the homochirality that we see in life on Earth is something that originates from outer space, which then again points to that meteorites and comets could play a major role when we start building up life on Earth. Where do these things happen? It happens in interstellar grains, dust grains that are sitting out there. It's extremely cold. It's ice with a silicate core, so everything goes extremely slowly, but on the other hand, we have lots of time. Billions of years in which this could happen, and we do see a lot of interesting hydrocarbons involved in the chemistry in these dust grains. And dust grains enter into meteorites, and in particular into comets. So there's a great chance that we would find a lot of organic material in comets. So what role do they play? There has been discussions whether the comets produced the oceans on Earth. It's been an idea that has been in favor and out of favor a lot of times. It was out of favor in the beginning because people thought that you could not be hit by so many comets that it would generate the oceans. Then they worked out the mathematics, and it turns out it's very easy to be hit with enough comets to generate the oceans. Actually, we are hit by too many. And the important thing is that comets do contain other stuff than water. We used to say at the time of our encounter with the Halley comet that comets were dirty snowballs. Now we are saying that comets are iced over dust balls. There are a lot of other material than ice in comets. Actually, we cannot really make a clear distinction between comets and asteroids. We now believe many of the near-Earth orbiters are actually burned out comets, that they contain so much silicate and organic material that there is a husk left over when the volatiles disappear. So now we think that if water comes, and a few years ago we disregarded again this idea because we measured the deuterium contents of comets and found out that there was much more deuterium in the comets we studied than there were in the oceans. So that sort of precluded that the connection was very good. But it has later turned out, because it was very difficult and insecure measurements, that now we are seeing several comets that have the same ratio between hydrogen and deuterium that we find in the oceans. So this is back in favor. And the important point in this connection is, of course, that if a large fraction of the water comes with comets, then we also get a lot of organic material. Because there's a lot of organic material in the comets. Actually, we get something like 10,000 more organic material than we find now on the surface of the Earth. But a lot of it, what impacts, will also disappear due to the violence of the impact. So it will disappear and be broken down and so on. But it's a possibility that the comets are an essential part of the production of organic material on the surface of the Earth. Now, an interesting question is, of course, that what we are discussing when we are looking at the origin of life is an event that took place billions of years ago. And comets only live for a very short time in the inner solar system. So what is the connection? Here you can see the Schwarzmann-Wachmann comet being broken down, and it will disappear in a few years. You can see the tails from all the remnants there, and that's the trail of the comet. And it's so that every time, for instance, a comet like Halley's comet enters the inner solar space, the sun will evaporate 20 or 30 meters of the surface. And as Halley's comet is only 10 kilometers and it comes every 76 years, you can work out that it will only survive in 10, 15,000 years. So it's a very short life inside, but comets have been arriving all the time. So let's look at Rosetta, with which we are going to look at the comet. And it contains a lot of scientific instruments, of which Cosima is going to analyze large molecules, so we can look if there are organic molecules coming out in the dust that surrounds the comet. This is an orbiter, it's not going to land. And there are a lot of cameras going to look at various wavelengths. I mean, like we have done when we flew by Borelli. You can see a lot of jets coming out with various contents. And if you look at it again in different wavelengths, one can find out what kind of molecules are coming in each of the different jets. And as you can see also here, and in the picture previously of 67P, what do I do now? What do I do now to get rid of this? I go here. So, you can see it has sort of a potato shape. And that's most of the comets have, because they are too small to have enough self-gravitation to reach the closed packed shape of the ball. So most of them are like potatoes. And as we saw, there's a lot of cameras here, but there are other ways that we can look at it. We can land on the surface with this lander here, Philae. And Philae can dig down into the surface, 20 centimeters or so. But 20 centimeters is enough, because every time the comet goes close to the sun, a lot of the surface will evaporate. So what we just have to do is to get below the thin layer that are influenced with the solar UV And if you can just go 20 centimeters down, you have pristine material and can look at how it's looking. There is another interesting thing. Let's see, where do we find it? Yeah. Yeah. The concert, which you have here, is actually only half an experiment. The other half is sitting on Rosetta itself, and the idea is that you will transmit radio and microwave through the nucleus. So whenever Rosetta is on the other side, you can send radio waves through the nucleus, and by looking how they are diffracted inside the nucleus, you can find out if the nucleus is one solid body or if it consists of cometismals, small chunks that are just together like a rubble heap. And this is important to try to analyze, because if it's a rubble heap, it has not had any chance of having enough heat to have a liquid inner. The interior could be liquid because the radioactive energy was much higher in the beginning of the history of the solar system, so it could have had an interior that were liquid, and that of course opens a lot of possibilities for chemistry that could take place. But if it's chunks broken up, then it has never been heated enough to be liquid inside. That's one of the important things we want to figure out. The drill will put material into various ovens and analyzers, so we can get a very good idea about the composition of the surface of the comet. And it's going to be very interesting to figure out and watch. Actually, we can see it because we have the orbiter taking pictures all the time. We can see this lander sitting on the surface as the surface is slowly disappearing beneath it. So it's going to be interesting to see if it can remain stable. So we hope to be able to complement this picture of Halley. And the thing is, of course, the history of the individual comets is very short, and we are looking at something that happened a very long time ago. But one has to envisage that comets are sitting in the outside of the solar system, practically unaffected by the passage of time. It's very close, no radiation, so it's only when they start their journey into the inner solar system that things are happening. So it's essentially pristine material that has been in stasis since the origin of the solar system, and then slowly are diffusing in here. So the idea is that what we are seeing in comets today is a good replica of the way comets acted in the beginning of the solar system history. So the origin of life as we know it today, we have the earliest signs where we can study carbon that looks like it has been made in photosynthesis, that is by organic material, 3.8 billion years ago. It's a study of minerals found on the Isua Peninsula in Greenland, and at the same time they studied the effect of this impact here, and it turns out that probably most of the projectiles that arrive in this late heavy bombardment must have been comets. And that also fits with the idea that the late heavy bombardment was caused by the big planets moving out in the solar system and disturbing all the ice bodies that were out there already, so they went into the inside, and many of them hit the Earth and the Moon. And it's a very big impacts, actually impacts that were so large that they could remove the water from the surface of the Earth. And one of these impacts, one from 65 million years ago, you might have heard of, the KT impact, the one that made sure I don't have 4 feet and a long tail, but instead is a mammal and not a dinosaur, although I'm old enough. But in the beginning, the impacts were much, much larger. And we are having a sort of a competing role for the comets. They were large enough to impact the Earth so severely that life couldn't start. On the other hand, they also provided the material that started the life. So that's a story we really want to be able to sort of trace in more detail than we have done so far. So that's one of the aspects, one of the scientific aspects of the Rosetta mission. Thank you.
Yes, we want to thank Ib Lundgaard Rasmussen. He's a senior scientist at DTU Space for a very exciting talk. And it's possible for you now. It's possible for you now to ask some questions if you want. You can do it in Danish as well, so that shouldn't keep you away from asking an exciting question, maybe. First of all, suddenly a lot of young people arrived, and including a cat. I love that. Which school are you from? Okay, yeah. Is it so that you, sorry? Yeah?
Should I just speak up?
Yeah, try to speak up.
Like, how much water did these comets bring in? Because it sounds crazy that the water came from the comets.
Why?
I don't know, it's just when I look at, there's so much water out there. So that was one question. And the other question I had was, on your last slide, you had something about, on the other axis, you had amounts of water evaporated.
Yeah.
So I was just wondering if you could explain that as well.
Okay. This one?
Yes.
Okay. You have an energy scale here, and you can convert the energy into how much water will it be possible to evaporate. And you know how much energy it takes to evaporate 1 gram of water, and then you can scale up and work out how much it will take. So the KT impact, the one that disturbed the situation on the Earth enough to kill off the dinosaurs here, roughly 0.5 meter of the water could be evaporated with that energy. But the big impacts here could take 3 kilometers. And why 3? Why not 4 or 5 kilometers? That's because there is no more water.
So it's evaporating the water from the comet?
It's evaporating water from the surface of the Earth.
Oh, okay.
I mean, impacts are, let me give you an example. When we flew Giotto past the Halley's Comet, it was hit by a stone that removed roughly 2 kilograms, crashed the camera, and sort of deorbited or changed the attitude of the spacecraft. And this stone that did all this damage was all of 40 milligrams. 40 milligrams for people that don't have a medulla weight in their head is roughly a rice seed. But it was coming with 70 kilometers a second. And if you see one of those, you better duck. It has 20 times the energy of a rifle bullet from an elephant gun.
Yeah,
So
we haven't.
If something comes that are 20 or 30 or 100 kilometers in diameter with that speed and hits the earth, there's a lot of energy deposited.
Thank you. And now we have a question from one of the students.
Et spørgsmål var også, hvor meget vand de der kometer indeholdet.
Ja, men det kan man jo hurtigt regne ud, altså hvor hyppigt bliver vi ramt af en komet. Lad os sige en gang hver 100 år eller sådan noget, ikke? Vi skal have noget i retning af 10/7 kubikkilometer. En komet kan være 10-100 kubikkilometer, og vi har 5 gange 10 år til at gøre det i. Så du kunne se, at regnestykket passer fint. Der kommer masser af vand.
Det kan I jo regne efter på jeres skole, om den holder. Is there any more questions? Otherwise, we will say, okay, sorry. Yeah.
You talked about the chirality of the organic molecules. Obviously, something I've missed out in biology, but is that? I think that's true for all of us. That
Yes.
yeah. So quite strange, and that's the reason why we had this problems with medicine that has a wrong chirality.
Yeah.
Okay.
The thalidomide scandal was one example. So all the amino acids are turning left, and all the sugars are turning right. So then their shape fits together. And the effect of a protein is very much depending on the precise shape that the molecule have, and it consists of maybe 100 different amino acids. So they have to fit together very precisely. So that's easier when you only have one type of amino acids to fit to. But at the same time, he also answers a question that my old teacher, Jens Martin Knudsen, always asked. He was very interested in Mars, and he said that when we find life on Mars, will it turn our way or the opposite way? If, as it looks like, the chirality originates in outer space, then Mars will turn the same way that we do.
Yes, we have one question more.
Bliver altså bare lige på dansk. Det der med impact energy, i forhold til, hvis vi nu tager sådan atombomben ved Hiroshima, ved du, hvad sådan forholdet er i forhold til, hvor meget energi, der kommer ud der, i forhold til 10^33?
Ja. Den her KT-nedslaget er cirka 10.000 gange større end Hiroshima. Den her, den er 10.000 gange større end den der.
That tells a lot about the perspective in it. Yes.
Så hvem snakker energikrise?
We will thank Ib Lundgaard Rasmussen many times for his talk. Thank you. And now our next speaker is Hans Jensen from Therma. He's a senior engineer, and I'll try to translate his title, and you can correct me if it isn't right. it must be something like Denmark provides power to Comet Hunter, I would assume. Okay, fine. Welcome.
Thank you.
We will just switch the computer. Thank you.
Yeah. So I will tell you a story about what it is that we have built here in Denmark that sits on board the Rosetta spacecraft. And I will also show to you how the spacecraft is traveling and how we will arrive at the comet and how the complete mission is done out there. Therma in Løstrup has built the power supply that sits on board the spacecraft. And what is a power supply on board a spacecraft? That is similar to what a power station is on ground, because that's the only power source that we have available on the spacecraft. It sits there and collects all the power that comes in from the solar panels, operates the batteries, and supplies all the equipment on board the spacecraft with electrical power. And this is worth to say that this is from the beginning, from the launcher starts from the launch pad and until the end of the mission 15 years later. So no failure, please, in that period. That's why this power supply is built in a completely different way than what you would see here for a ground application. Nobody can touch it when it's first up there. So there's nothing called service. So Rosetta mission was the first one to be powered from solar panels that far distance of 5 AU from the sun. 1 astronomical unit is the distance we have from the Earth to the sun. So we are 5 more deep out in the space when the Rosetta comes to its outmost point of the orbit. So, and said, this is the first time that spacecraft shall be supplied by electrical power from solar panels that far out. Earlier missions, flying even deeper than that, has typically been powered by a small atomic power station. That makes it fine. We did not have that technology in Europe, and we did not want to develop it either, so it was decided that we will supply it from solar panels. And that was a very good thing for us in Therma, because this is what gives us an opportunity to build the power supply for that mission. An artist has shown here how he thinks that the landing might be on the comet that we'll see on the 28th of November this year. And if it really looks like something like that, that will be very exciting at that time. But that is one of the purposes of the mission, to set down a small lander on the surface of the comet. So now back to the solar panels and the mechanisms there. The spacecraft needs 500 watts to operate. And to keep safe at the coldest part of the mission, we need about 400 watts. When we are at the outmost of the orbit, the 5 astronomical units away from the sun, we can only from the 65 square meters of solar panels only generate 400 watts. 400 watts is all what we can get there, and that's about the same as what a small equipment in our kitchen can use at home, so not very much power. So 65 square meters is necessary to give us the electrical amount of power, and it is obvious that it is important that we get all the power that we have on the solar array, otherwise that should be even bigger than that. Solar arrays will start at a temperature of 50 degrees when we start here around the Earth. And as we come deeper and deeper into the space, temperature will decrease down to minus 130 degrees Celsius. And that changes a lot of the characteristics on the solar panels that makes the complete mechanism change. So the electrical mechanism that extracts the power from the solar panels has to take that into account. That's why we need what is called a maximum power point tracker that can do that by itself and always ensure that we take the absolute maximum that we can get off these very large solar panels. And this is where we came into the game. This is the only electronics diagram that I will show, I assure you, but you need to see that one because it'll help me to explain how we make the things in a way so we can be so sure that it will not fail during that long mission time. Such a mission has a price of about 1 billion euros, and nobody will accept that we just lose it by a single failure somewhere. That means all equipment that sits on board that is important for the mission is, we have two of them, one parked not powered, another one powered, and if the one should fail, if the first one should fail, it is by ground command switch it off and the next one switch it in. We cannot do that on the power system. That's completely out of the question to do on the power system. And why is that? Because we have only these two solar wings and the power supply has to be connected to that. So if a first one power supply fails, who should ever switch the next one on? There's no ground contact at that time. So the power supply has to do it by itself. That's why this equipment is much more complex than other equipment on board. We have to build this double or redundancy into the electronics function. As you can see here, we have 3 blocks sitting and interfacing to one of the solar panel. And that's 3 independent functions that votes against each other, who agrees on the decisions that we have here. And when 2 of them agree on what to be done, they are the right. When we started developing this power supply unit for Rosetta in '98, we were required to give it a mass of no more than 8 kilograms. The previous equipment, not even being less complex than that one, had a mass of 25 kilograms, so we had to figure out something, a new method to build. And we developed a new modular technology that we put together into a backplane, put a top and bottom plate on it, and we have a complete power unit. Quite simple, isn't it? But nevertheless, we were the first to do this. And the secret behind it is that we developed a new technology, a new way to mount our high dissipating power components in a way that we can also ensure that all the electronics can be built much more compact than ever done before. This is how such a module looks like. These devices I talked about sitting there. Such a one takes 250 watts in from the solar panels and give it to all the other electronics. So the key to win this project was to be able to demonstrate to the customer that we have the idea, we know how to secure that we can build this maximum power point tracking function in a way so we can declare for sure that no matter what kind of failure, what single failure happens in that equipment, we will still survive and be able to extract the full power from the solar panels and into the equipment. So that's why we have 3 sitting and voting together to agree. So if one of them do not agree with the others, it is simply some way excluded from that decision. We were the only company in Europe that could explain how to build this. We did not win it on the price. We won it on the quality that we can demonstrate that we can build into the electronics. So now coming to the traveling out to the comet. We see here the spacecraft was launched in 2005, and coming up and making swings around the Earth. Next, we do here a swing by Mars, and later on again one more swing around the Earth. We now gained sufficient energy to get out to an orbit that even exceeds the Mars orbit, as we see here. Getting back into the Earth and making a third swing again here. Now we gain sufficient energy to get out to an orbit that is very similar to the one that the comet is following. We have a little more speed than the comet, so we will get into it after some traveling time, and it is around now that we will meet it. On the 20th of January, we came out of the eclipse of the hibernation mode that I will tell about later on. We will arrive at the comet in August, now in August, at about 5th of August. And the lander will be deployed and put down on the surface of the comet the 28th of November this year. Rosetta and the lander, they will follow the comet in a path through this, getting close to the sun. End of mission will be about December 2015, but let's see, we've seen before that such mission has been extended because they were still interesting to follow. I have a good contact in the European Control Center in Darmstadt, south of Frankfurt. That's from where all is operated here in Europe. He regularly tells me how the situation is on board the spacecraft and how the thermal power supply is working up there. And I assure you, I copied this sentence as he sent it to me without fixing anything to it. And he was telling me that the power supply unit is their favorite unit because it's always doing very well. So I was very happy of that. So now, as the spacecraft travels deeper and deeper into space, it becomes colder and colder, and the sun electricity that we can generate on the panels decreases over time. And at a certain boundary, we will have less than the 500 watts that we need to operate the complete spacecraft. 500 is the minimum on which we can operate everything, operate the radio transmitters to keep contact to ground, and also to operate all the so-called attitude control system that ensures that the spacecraft is sitting in the right position and having the solar panels looking perpendicular to the sun. So when we came to this limit here, something else had to be done. We had to switch everything off that does not necessarily need to be powered. Switch off radio transmitters, switch off attitude control, so the spacecraft is left on its own, and then traveling for 2.5 years through the very cold period, getting down to the minus 130 degrees, and came out again here to the 20th of January this year, and came to life, back to life again. So a small timer unit had to wake it up because the spacecraft is left with no ground contact at all. the spacecraft had to be left in a way so that it is perpendicular to the sun. And where is it that we get the minimum power? Well, that's when we are out at the outer point. But this had to be ensured that the spacecraft is then aligned from the beginning, so we will have correct alignment at that time. This was done in a very special way that I can demonstrate. I have with me here a model of the spacecraft, the solar array wings, the body. So the spacecraft was simply left in and put into turning around itself like a wheel, and that makes it stable, so we are sure that it will not turn away from that. So simply brought into rotation about itself and left there for 2.5 years, so that it comes out again after 2.5 years and still sits in the right direction to the sun. And this animation just shows about the rotation speed that it was brought into. Note that at that time that this occurs, already that time the radio contact to Earth is already lost. So the spacecraft had to do this itself after we lost contact to it. So actually at that time even nobody could know did it happen or did it not happen. But it did. So 2.5 years later, the spacecraft should wake up again. It has a small alarm clock built into it that was programmed to wake it up at 10 o'clock, 20th of January 2014. A lot of things to be done when the spacecraft came back to life. It has to find out, or first of all, to decrease the rotation around itself, then find out how am I oriented in space? How is my attitude? Because it has to figure out what direction perfectly to line up to get perfectly perpendicular into the sun for the solar panels. It has also to find out where can I find the Earth, because the parabola antenna has a very narrow sight of angle, so it has to know exactly where to point to, and this is figured out by star trackers that we just saw in operation here. Star trackers take a picture of the stars seen from Rosetta in that direction, looks into a map of the stars and find out where I am looking to and how to change my attitude so I get the right direction into the Earth. This is now done. After that, the antenna will be corrected and point perfectly to ground. All this was counted together and would take from 10 o'clock in the morning and until 6:30 in the evening, with an uncertainty of 1 hour. So we knew that the signal could come 6:30 or latest 7:30. We were 49 minutes into that 1 hour before it came up, before it showed up. So it was some exciting. Two big ground stations were looking in the direction where Rosetta was expected to appear. The big 70-meter antenna in Goldstone and one similar in Canberra in Australia. And one thing to notice is that such a big antenna has a very, very narrow angle of sight. It's like looking up to the sky through a small tube. So somebody had to figure out exactly in what position will it come back to life after traveling 2.5 years. So they found it, both of them, and we saw on the screen that now the small green thing came up and showed that there was a radio transmission now from the Rosetta. A very good thing, because if that did not happen, we would not have the exciting mission that we have today. All this navigation, the positioning of the spacecraft speed, the speed direction, this is all measured here from ground, from these ground stations. 3 are supplying, one, the Goldstone, the Madrid, and the Canberra stations. They can figure out from the radio signals where exactly the spacecraft is, which speeds it is traveling with, and in which direction. Now and then we use 2 ground stations to look to the spacecraft. 2 ground stations will have a distance on ground of 5,000 kilometers. At the time now, Rosetta is 550 million kilometers away. That gives a triangular, a very, very narrow one, but nevertheless, this can be used to calculate the perpendicular speed compared to ground direction. Very complex mechanism and fantastic that can navigate precisely enough to get it to the comet. It was figured out where to find the track of the comet by the Rosetta camera. During March should be the best chance to see it. We are actually today only 1.5 million away from the comet. That's not far compared to the distance already traveled. So, and here in end of March, Rosetta actually took a picture of the stars in that direction, and the comet, named after the Russians that I cannot say the names of, so it's 67P, was identified to be here. Well, the circle is put on to give a mark on that was not on the real picture. So that was the evidence that Rosetta is on the right course, that we're traveling the right direction. Well, maybe not a big surprise, but anyway. So now here in May, a lot of or more breakings are performed to decrease the speeds as we come closer to the spacecraft. Today, as mentioned, we are about 1.5 million kilometers away. At the end of May, we will be approximately 500,000 kilometers away from the comet. End of June, we will be down at 50,000 kilometers. 2 breaks will be performed there to decrease again the speed of the Rosetta compared to the comet. And in July, again, three maneuvers. And at the end of July, we will be very close to the comet. And coming close to the comet, Rosetta shall bring itself into an orbit around the small nucleus, circulating around it. And while it is circulating around the comet, the camera shall take pictures of all the surface of the 67P, mapping all the surface and send this back to Earth, so people can sit here in control center in Darmstadt and figure out where is a safe place of putting the lander down. And it will be very exciting to see how they will decide this before November, because most likely where it's most interesting to put down the lander is probably also the most difficult or dangerous area. So we will see how this will be decided. When it is decided and planned, and as said, it is scheduled today. The best known is 28th of November. It's not a very fixed date. It might vary some, but that's the most likely today. Then Rosetta will be brought in, make another course correction, bring it into the right path around the comet, and release the small lander. That will travel for 9 hours before it gets down to the comet. We will see here on the next how this will occur. The small lander releases from the mother spacecraft and falls slowly down to the surface. As said before, the mass of the land is about 100 kilograms on Earth. On the comet, it will have a mass of 35 grams, like a small letter. So note here that 2 arrows will plug down into the surface of the comet, pull the spacecraft back to secure that it will not jump away again. Because if that was not done, just the bouncing of the legs would be enough that it would disappear again. So this is the way that it's planned to secure that it will stay on the surface and stay there. And the last one, we see some of the final maneuvers that the Rosetta will perform. It has on board the spacecraft fuel for burning a small rocket, mechanism that can change course corrections. These fuel tanks was actually the main reason that we had to keep the inner temperature of the spacecraft around at plus 20 degrees during the very cold phase, because they cannot sustain this very cold. So this fuel will be used for making these course corrections as spacecraft will move closer and closer into the comet, bring itself finally into an orbit. As I understand it, the operators will find out over time how close can we get, how close is safe enough, because do not want to get too much in contact with the tail of the comet, because that can be a lot of dust and material that is blown away from the comet. But getting closer and closer into it, and Rosetta has a number of instruments, 18 in total, that it will operate from the distance of orbiting. Rosetta will at the same time act like an retransmission station, because the small lander that sits down on the surface cannot communicate directly to ground. So Rosetta acts like a relay station for that period. That was the end of my presentation. I think that we have time for a few questions.
Yes, we want to thank very much for an interesting talk. And actually, normally you say you look after a needle in a haystack. I will say this mission is a kind of symbol for that. And I can also say that the work concerning this mission must be like, you can't fail the precision. So we're looking forward to hear more. And now I'll give you, our audience, the opportunity to ask some questions. It can be in Danish if you wish. I can then say that I'll turn back to you. I love your T-shirt. Every mission that is sent out in space has their own logo, and I couldn't resist seeing those sitting 2-person or maybe 3 with a text behind the back. One school, 1,000 opportunities. That's a nice logo. And you got a question?
Det er mere, hvorfor, når det sidste slide, du viste med, hvordan den gik ind mod kometen, hvorfor ikke gå lige mod, og så til sidst ændre den og gå i cirkel rundt om? Hvorfor skulle den lave de der trekantede?
Det hænger sammen med, at fra den afstand vil man gerne fotografere mere og mere af overfladen efterhånden, så man kommer derned. Så man egentlig husker på, at den lille komet roterer omkring sig selv. Så ved at lave den manøvre, får man mulighed for at se den fra alle sider ved at lave den underlige manøvre med at ændre kurs. Og så kommer man også, hænger også lidt sammen med, at det sker, mens spacecraften bevæger sig udefra og ind imod den, at man der laver den manøvre for at få den at se fra forskellige vinkler. Jeg forstår det som, at det er mere en fordel, end bare med at flyve direkte hen til den for at komme i kredsløb. Som jeg nævnte, så vil man også gerne nærme sig den lidt forsigtigt, så man er sikker på, at man ikke bringer fartøjet ind i noget, som den ikke kan tåle. Fordi det er jo kendt sag, at kometen afgiver en hel masse gas og støv fra sig, og det tåler spacecraften ikke rigtig at komme igennem. Det skal man i hvert fald være forsigtig med. Så det er sådan en kombination af det, der er årsagen til, at man vælger at gøre det på den måde.
Jeg tænker lidt, hvis jeg må spørge, hvor lang periode har man til ligesom at finde det mest ideelle tidspunkt til at lande? Altså, hvad er vinduet der?
Rosetta kommer i kredsløb omkring kometen fra den cirka 5. august. Og på det tidspunkt starter man sådan set med at tage billeder af overfladen. Og først på et eller andet tidspunkt, når man synes, at billedkortlægningen den er god nok, så vil videnskabsfolkene begynde at diskutere, hvor er det så, vi skal sætte det ned hen. Jeg kender ikke nøjagtigt tallene på det, men jeg vil forestille mig, at i hvert fald har en måneds tid til at afgøre det, efter at kortlægningen er færdig, inden man bestemmer sig for, hvor man sætter den.
Så håber jeg, at de kan blive enige om tidspunktet.
Ja, det er spændende at se.
Ja, det gør det. Vi glæder os til at følge det, og der er et spørgsmål mere.
Ja.
Hej, det var på en af dine slides, hvor der stod, at det cirka er 45 til en times video med forbindelse til satellitten. Hvad er det gør, at det kun er en time?
Det skal jeg lige høre en gang mere.
Altså, der var en af dine slides, hvor der stod, at der kun var 45 til en times forbindelse til satellitten. Hvad er der?
Det tror jeg nok, der hvor jeg har det, der hvor det står på, det er på den tid, hvor det er der, hvor den kommer ud fra dens såkaldte hibernation, altså fra dens vinterdvale, kunne vi kalde det. Der på det tidspunkt, hvor den kommer frem og begynder at sende til jorden, der har man ikke ret meget mere end den tid at gøre med, fordi man er ikke sikker på, at der var strøm nok til at kunne operere i længere tid. Det havde faktisk kun der omkring en times tid at gøre med at kunne sende signalet til jorden, inden man kunne godt komme ud for at være nødt til at stoppe den igen, for at den ikke skulle komme under det kritiske niveau for effekt, der er til rådighed. Så det er der tallet, det stammer fra. Men det viste sig at være ikke nødvendigt. For det viste sig faktisk, at effekten, der kunne hentes fra solpanelerne på det tidspunkt, der var faktisk noget større end det minimum, det kunne have været. Sådan er det typisk. Der fandt ud af, at der var faktisk nok til at operere den kontinuert for, så man kom aldrig ind i den der tilstand med at kunne køre den kort tid ad gangen til at begynde med. Så den gik i gang med at operere kontinuert.
Ja, hvis der ikke er flere spørgsmål, der er et mere.
Bliver det livestreamet, når den lander?
Det ved jeg ikke. Det håber jeg, men jeg tvivler næsten på det. Men jo, jeg skal. Vi må se. Jeg ved det faktisk ikke, hvordan det kommer til.
Der er tradition for, at tingene bliver livestreamet. Det er der tradition for. Og
hvis det kan lade sig gøre, så bliver det.
Ja, det tror jeg. Det vil der blive arbejdet for.
Problemstillingen er bare, at den datatransmissionshastighed, der er derude fra, den er altså meget, meget begrænset. Så jeg er ikke helt sikker på, at man kan følge med til at gøre det live. Det er faktisk helt tvivl meget på, om man kan. Jeg tror på det tidspunkt, der har man højst noget, der ligner 20-30 kilobit per sekund at gøre godt med. Så det rækker ikke til det helt store, i hvert fald ikke den helt store opløsning i billederne. Men vi må se, hvordan det kommer til at gå.
Tusind
Men i
tak.
hvert fald, så skal jeg sige, følg godt med, når vi kommer hen til den 5. august. Fordi der kommer der sikkert en hel masse omkring det, når satellitten bliver bragt ind i sit kredsløb omkring kometen. Og jo helt sikkert den 28. november, det bliver jo det bliver en dag med masser af medieomtale på det, er jeg sikker på. Så vil jeg også gerne lige inden slutter lige fortælle jer, at den strømforsyning, som I faktisk ser her, den har vi i dag flyvende 3 eksemplarer af. Der sidder en på et fartøj, der kredser omkring Venus, og der sidder en på et fartøj, der kredser omkring Mars, og så den her, vi har på Rosetta. De er ens alle 3, og de har fungeret nu i cirka 10 år hver, så vi har omkring 30 års driftstid på dem. Vi ved med sikkerhed, at der er ikke sket nogen som helst fejl på noget af det nu, så vi har ikke brugt af de reserver, der er bygget i den, og det håber vi også, vi aldrig kommer til.
Så har vi jo sådan set også forklaring for, hvorfor I blev valgt.
Ja, det kan man sige.
Fordi det var jo i udbud, så det var jo fint.
Det ser ud til at valget var rigtigt.
Ja. Stort tak. Ja, og spændende. Tak.
Ja.